Hello, everyone. Welcome to today's Tech Excellence session. As you already may know, our vision is to raise the bar of technical excellence across the world. So, here is our organizer team, Valentina. Valentina is founder and organizer at Tech Excellence. Daniel, Oliver, and myself, we are co-organizers and co-hosts. We already had a lot of great speakers this year and keep having a lot of great sessions and speakers this year, so stay with us. You can find us on different social media platforms such as Meetup, YouTube, LinkedIn, Twitter or newly X, GitHub, and Discord. Our sponsor is Optimum and our partner is QE Unit. So, today we are very happy to introduce Vlad Khononov. Vlad is a software architect with over 20 years of industry experience. He maintains an active social media career as a public speaker and blogger, and moreover, Vlad is an author of the well-known book Learning Domain-Driven Design and his newest book, Balancing Coupling in Software Design, which is also the title of his presentation today. But before, I would like to remind you, you can leave your comments and questions anytime in the chat down below. At the end of our session, we'll have a 30 minutes time slot for discussions. So, Vlad, enjoy your presentation.
Thank you, Alina. Yep, I think you can see my screen right now, so good evening, good day, good morning, I don't know, depends where you are. I'm in Israel, so here is good evening. My name is Vlad, and as Alina mentioned, I've written a couple of books. The latest one is Learning Domain-Driven Design. I really hope that you already read it because some of the things that I'm going to talk about today, they are somewhat going to be related to domain-driven design. But if not, that's fine. Nobody's perfect. Just kidding. I'm still going to introduce the discussed concepts. Now, I am a domain-driven design fanboy, but today I'm not going to talk about it. Instead, I want to discuss another topic that I'm really passionate about, and that's coupling. Now, turns out I'm so passionate about coupling that I ended up doing a very stupid thing, and that's writing a book. The book is called Balancing Coupling in Software Design. The manuscript is almost ready. It's in the editing process right now, which means soon it will go to production, but today I want to give you a preview of the book's material. Now, preview doesn't mean sales pitch. No. My goal is not to convince you to pre-order it, but my goal is to give you tools, then you can use them in your day-to-day work right now without waiting for the book to be published. So, coupling. I don't know about you, but I've always been told that coupling is bad. Coupling slows us down, it cripples our systems, and software engineers, when they're working on a system that actively resists changes they want to make, of course they're blaming it on coupling. As a result, not surprisingly, what do we want to do about coupling? Well, of course, we want to decouple everything. We want to take everything and break it apart into those tiny boxes. In these boxes, they can be classes, they can be modules, serverless functions, microservices, whatever. The underlying motivation is always the same. We want to be able to change and evolve each one of those little boxes independently without affecting the rest of the system. But what results are we getting by following this somewhat simple reasoning, by focusing on the size of these boxes? Well, in many cases, we go from coupled piles of code to distributed piles of code. And that's not surprising because, as my friend Matthias says here, as small as possible is almost universally a bad advice in software design. Or, as Nick Tune put it, there are many useful and revealing heuristics for defining the boundaries of a service. Size is one of the least useful, and yet we keep on doing that. So I know it may sound controversial, but instead of fighting coupling, in this talk I want to show you a different way of thinking about it. And I'm going to try to convince you that you can use coupling as a tool for designing modular software systems. So this is going to be our agenda for the next 40 or something minutes. I'm going to start by defining what is coupling exactly. Then we're going to see how coupling manifests itself in different dimensions. And finally, I'm going to combine these insights to turn coupling into a tool for designing modular software. So let's get started. What's coupling? If we go to the lexical origins of this word, it will take us all the way back to Latin, where it was composed of two words, co and apere. Co-apere meaning fasten together. In other words, if two things are coupled, it simply means that they are connected. And that makes coupling a ubiquitous phenomenon. It is everywhere. This clicker is coupled to my computer right now. Organs in our bodies are coupled to form us, living organisms producing code. For that matter, a car, a city, a human body, an organism, a company, all those all those systems, they're held together by coupling. You cannot build a system if all of its components are disconnected. On this slide, for example, that's not a system. That's just a group of some components in the same boundary, but they're not working together, and as a result, they are not providing any value. It's just a bunch of fully independent and fully decoupled entities. But that's not a system. For a system, we need these relationships, these connections between the components. And these connections, that coupling between them, that's what makes a system greater than the sum of its parts. Therefore, it makes no sense to try and completely decouple everything, because coupling is an inherent part of system design. Instead, let's try to evaluate those inner component relationships and see if they're working for us or against us. Now, let me show you what I mean by that. Let's say we have the two components shown here. The downstream component references and thus depends on the upstream component. That arrow between them, that relationship, it defines how these components are integrated. It defines how change in the upstream component is likely to break the integration and require cascading changes in other parts of a system. As Michael Nygaard says, coupling defines the components' degrees of freedom, how freely the components are able to change without affecting the rest of the system. In other words, the way the components are integrated defines what changes can we make in the upstream here without being afraid to break the integrations with other downstream components. Now, to evaluate the effect of coupling, we have to understand its dynamics, how it works and how it manifests itself. And the interesting thing is, we're used to think about coupling as something unidimensional, as if coupling exists or it doesn't. But it's more complicated than that. Coupling can affect a system or a system's design in three dimensions: space, time, and the combination of these two. It's gravitational force or strength. Strength is probably the dimension that is usually the most associated with coupling, so I'm going to start with it. In a sense, strength is a sort of gravitational force that pulls components together. It defines what is the impact of a change in one place of a system is going to be on its other components. The higher the strength, the more cascading changes will follow. Assume we have these two components here, and they're connected. But at this stage, it doesn't really matter what these components are, whether these are classes, modules, services, or whole systems. Also, the nature of that relationship between them, it's also not important. It can be synchronous or asynchronous. However, what is important is that that line, that pipe between them, is used for exchange of some energy. And My question to you, what is that energy? Think about it for a few seconds. When you have two connected components in a system, what energy do they exchange between them? And I guess at this moment you're thinking about information or data. And of course, that's true because, well, if components are connected, they have to work together, and as a result, they have to exchange some data, right? For example, one component can issue a command to another one, or it can use that connection to read information from the other component. That's, of course, important and crucial for the system to work. However, that's not the most interesting part. In addition to data, there is something else that is being exchanged between these components. And you know what, take a few more seconds and think what that is. What is behind that question mark on this slide? And at this moment, I hope you're thinking about the don't repeat yourself principle. And we know that don't repeat yourself principle is not about code, but it's about knowledge. And that's the second energy that is being exchanged between coupled components. That knowledge can describe what a component is doing, its business functionality, or it can describe how it is implemented. Overall, there are different degrees of the amount of knowledge that can be shared between connected components. Now, to evaluate that amount of knowledge, we have a few methods, a few models that were introduced as our industry evolved. It started in late 60s with the model of coupling in methodology called structured design, and then in the middle of 90s, Miller Page Jones introduced a model called connaissance. Now, these two models are super important. However, there's a problem with them. The first one is based on terminology used in languages such as COBOL and Fortran. And that makes it pretty hard to apply it in our modern systems. Connaissance is the same story. Although it can be used in some contexts, it is problematic in other contexts when we're talking about modern software systems. Now, I was thinking that if the first model was introduced in 60s, the second is 90s, that gap of 30 years between them makes now the perfect time to start thinking about a new model of evaluating coupling. And that's something that I call integration strength. That's a model that I've been using for some time now. I find it way more practical and useful than using either structured designs, coupling, or connaissance. And it's in its nature, it basically remixes or combines and compresses the previous two models into something that is more practical, something that is way easier to use and to apply in day-to-day work. Now, connaissance has 11 levels of interconnectedness. Structured design has 6. Now, integration strength makes it simpler. It compresses those levels into 4 types of knowledge that can be exchanged between connected components: intrusive, functional, model, and contract coupling. Let's go over them and see the differences between them. So first, intrusive coupling. As the name suggests, that's not something that you want. It's not something that is planned, and probably there are some rules being bent when intrusive coupling is being introduced. What it means is a downstream component introduces a dependency on a private interface or an implementation detail of the upstream component. In other words, instead of using its public interface for interaction, it uses its implementation details, its private interfaces. A good example is reflection. If you're working in Java or C#, you can use reflection to read or write a value of a private field, right? Or you can call a private method. Well, probably those fields and methods are made private for a reason. However, you can still do it. You can still use reflection and work with them. Once you do that, you're introducing intrusive coupling. Now, the implication of intrusive coupling is that we have to assume as if all knowledge about the implementation details of the upstream component are shared with the downstream component. That means the authors of the upstream component cannot change it freely. They have to think twice whether a thing they're changing can affect the downstream or not, whether it's going to break the integration or not. Sorry. And of course, such a relationship, such integration between two components make that integration fragile and implicit. The authors of that upstream component, they might not even be aware that that integration takes place. So again, reflection, private interfaces, or if we are talking about microservices, well, we often talk about databases in microservices, that no other microservice should access another microservices database. Why? Because that's an implementation detail. Accessing it introduces intrusive coupling. When a downstream is aware of your implementation details, you're no longer able to evolve those implementation details if you need to make some changes. Again, you have to assume with this kind of a relationship that all knowledge is shared. Next one is functional coupling. And this one means that the connected modules are implementing closely related business functionalities. Its practical implication is that the same business requirements are going to trigger simultaneous changes in both components. For example, closely related business functionalities can be found in domain-driven design's subdomains. I usually define subdomains as sets of interrelated use cases that function on the same set of data. That makes them functionally coupled. Another example from domain-driven design of functional coupling is the aggregate pattern. What do we put in an aggregate? Only the operations that require strong consistency. That strong consistency put them in the transactional boundary of an aggregate, and that's probably the highest level of a functional coupling. A rather extreme example of functional coupling would be two modules implementing exactly the same business logic or business algorithm in two places in the system. When the requirements for that business logic change, the modules have to change together, because if they don't, the system is going to end up in an incorrect state. For example, let's say we have a business rule implemented both in front-end and back-end. Now, software engineer updates the back-end but forgets about the front-end. What's going to happen? Well, front-end says, yeah, your command is going to work. Well, the backend says, no, I'm not going to execute it. Now, what's more interesting about functional coupling in this case is that modules that implement duplicated functionality, they don't have to be physically connected to each other. They can be completely different services or modules in the same system, not connected to one another. But as long as they have to change because of the same changes in the business requirements, they're functionally coupled. And again, as I said in the intrusive coupling, that relationship is pretty implicit. So functional coupling is pretty implicit as well. Again, think about that last example. You have duplicated functionality in unrelated parts of the system. A lower level of integration strength is model coupling. This one means that the components are based on the same model of the business domain. Now, if function coupling was more about the behavior of a system, model coupling is more about data structures that are used to represent the entities that belong to the system's business domain. Now, me wearing my DDD hat right now, I'm going to tell you, model is crucial for a successful software system. That means that a model should be evolved as you get more insights into the business domain of the system. Now, when you have model coupling between components, it can make it hard to evolve that model because suddenly you have to implement the change in multiple places. So, well, I've been in that situation, and yeah, sometimes you just say, okay, that's just semantics. We'll just leave it like it is right now. So again, model coupling is introducing dependency on the model of a business domain. And again, if I'm wearing my domain-driven design hat right now, a bounded context is the boundary of a model. It defines that only what resides within the bounded context should work with the same model. Everything outside of it, other bounded contexts, they should use other models that are more optimized for their needs. And finally, the lowest level of integration strength is contract coupling. Here the components are integrated through an explicit integration-specific model that is decoupled from their implementation model. Think of it as a model of a model. The model of the business domain in this case can change freely because it's just another implementation detail of the upstream component. It's not being shared with downstream components. Instead, an integration contract, another model that encapsulates the implementation model, is shared for external parts of the system. Now, in that case, well, I can evolve my internal model. All I should care about is that, yeah, I just need to translate it into the integration model. Now, in the language of patterns, we can think about, first of all, a simple DTO object. When you introduce a simple DTO, many people say that it's pointless, it just copies the same data. Well, the idea is to introduce a data transfer object as part of your integration interface that will allow you to evolve the implementation model freely without being afraid to break the integrations. Other patterns that what they actually do is introduce contract coupling are domain-driven designs anti-corruption layer, open host service published language that's by the book example of a contract, of an integration contract. And you can even think about the facade pattern as an integration contract. So this one is the lowest level of integration strength. And this means that it shares the least amount of knowledge. So if we compare these four levels, all of them reflect the amount of knowledge that is shared across components' boundaries. It also reflects how implicit or explicit the interfaces are. Intrusive coupling, it shares the most knowledge about how the upstream module is implemented, while functional coupling reduces that knowledge from how the implementation details, how the module is implemented, to what that module implements. It shares its functionality instead of its implementation details. Model coupling, this one reduces the knowledge to the model of the business domain that is being used by the upstream component. And finally, contract coupling minimizes the interface to share the bare minimum needed for the integration to work. It encapsulates the most amount of knowledge about how the upstream component is implemented. Now, let's see a few examples of this model in action. Now, I already mentioned that when we are designing microservices, we don't want to access another microservices database directly. And I want to use that example as a running example here. And the thing is, I used it as an example for intrusive coupling. However, the devil is in the details. Let's see. So in the example I used, that database was never intended for integration. And of course, that makes this intrusive coupling. Again, two microservices. The upstream has a public interface, but the downstream, instead of calling it, just goes to its database and fetches whatever data it needs. That's intrusive coupling. However, what if the authors of the two modules had a conversation and agreed that, yeah, we have to work on the same data. And they agreed that a database is going to be shared between them. That makes that relationship functional coupling. Because again, it's not intrusive anymore. It was decided that the database is going to be used as communication mechanism, and the two components are modifying the same set of data. The fact that they're working on the same data means that they're implementing closely related business functionalities. In other words, functional coupling. Now, what if that component A on the left side it's a BI system, business intelligence system that, you know what they do usually, they just import all the data from operational systems and use it for analysis. Well, that's a by the book example of model coupling, because what they're doing is they're coupling themselves to the model used internally by the operational system. Again, when the authors of the operational system are going to change the model, they're going to rename fields, for example, or remove fields or add new fields. Those changes to the model have to be coordinated with component A, BI system in this case. And finally, what if the database contains integration-specific data? What if the authors of component B in this case, they said, hey, this database contains data in the format that is optimized for integration. Don't bother me with your APIs. Instead, here's the database, go use it. That's an example of contract coupling. And by the way, if the previous example was of how typical data lakes work, this one is an example of the data mesh pattern or architecture. In data mesh, we use databases to share analytical data. It's okay to expose it in the database because it's intended for it. It's intended for integration. So that's contract coupling. And you know what? A few more words. If we think about databases, then in a sense, we can say that if we have a message bus or a distributed queue between two components of a system that are integrated asynchronously, that distributed queue, in a sense, it acts as a database. Yeah, its interface, its storage format is very, very limited, but it's still supposed, its goal is to store data. So again, in this case, that's contract coupling. Now, let's say that we have a system with two components, and the strength between them is intrusive coupling, the highest one. Does that mean that the design is necessarily bad? Well, if the answer was yes, I wouldn't be asking this question. So the thing is, we're still not ready to answer that question. We have to explore more dimensions of coupling. And the next one is distance. And turns out the physical locations of components in a code base, it also affects their level of coupling. The connections between a system's components, they can span different distances. These distances are closely related to what we usually call levels of abstraction, and they can span, for example, methods or classes, namespaces, modules, microservices, or whole systems. Now, what do we do with that? What do we have on that vertical axis? What's the implication of that distance? If you look on this chart right now, on the left side, here we have components located really close to each other, while as we go right, the distance grows. So what's the implication of that growing distance? Well, that is coordination effort that is required to implement a change. If we have a change in the system that affects coupled components, the longer the distance between these coupled components, the more effort we will need to invest to coordinate and implement that change. So in other words, we can say that the cost of making a change is proportional to the distance between the components it affects. The larger the distance, the more expensive the change is going to be. Now, that's not the only interesting effect of distance. Another interesting effect of distance is an inverse one, and I call it life cycle coupling. In other words, it reflects how interrelated the life cycles of the coupled components are. And as the components are located closer to each other, the higher the chances that changing one of them will inadvertently affect other components as well. For example, if you're changing a method of a class, well, chances are that that change is going to affect other methods of the same class. And again, the closer the elements are, the higher the probability of such collateral changes. And of course, if components share the same life cycle, that means that they have to be evolved, tested, and deployed simultaneously. And again, that further limits the possibility to evolve them independently. As life cycle coupling is higher, our ability to evolve them independently is reduced as well. Now, interestingly, the life cycle coupling is affected not only by the level of abstraction, but also by the organizational structure of the company that implements the system. And that's best illustrated with an example. Let's say that we're here on the right side, on the microservices range, which signifies quite a big distance, right? However, think about an example of having to change two microservices simultaneously. However, in one case, the two microservices are implemented by the same team, and in the second case, the two microservices are implemented by two different teams. Well, clearly, in the second case of multiple teams, we'll need higher coordination effort to implement that change. Thus, again, we're getting larger distance despite the fact that we are talking about the same level of abstraction. Now, let's say that we have two components, component A and B. They're connected as using functional coupling, which is quite high on the integration strength scale. And these components are actually implemented in different systems. So what we have here is huge distance between them. Let's assume that that functional coupling is, in this example, is about duplicated business logic. So we have duplicated business logic across an immense distance, two different systems. And of course, this design sounds bad, but is it? Think about it for a second. Is it necessarily bad? Think also about another question. If a tree falls in a forest and no one is around to hear it, does it make any sound? Probably not. It just creates vibrations of the air. Same thing here. If strongly coupled components never change, well, who really cares about the strength of that coupling? If they don't have to change, we are never going to experience the cost of that coupling. And that takes us to the third dimension, the dimension of time or volatility. And the main question here is, how often do the coupled components actually change? Well, as the saying goes, it's difficult to make predictions, especially about the future. However, we have some tools that can help us to estimate the volatility of components, to estimate how frequently they are going to change in the future. One such tool is Worldly Maps, and another one is domain-driven design subdomains. And as a domain-driven design fanboy, guess what I'm going to show on the next slide? Yeah, subdomains. So, according to domain driven design, a business domain of any system is composed of business building blocks that we call them subdomains. These building blocks, as I said earlier, they represent closely related use cases. Interrelated use cases that probably work on the same data and probably are going to be affected by the same changes in the business requirements. Now, what's interesting for us here is that not all subdomains are equal. Actually, we have three types of subdomains: core, generic, and supporting. Core is all about the company's competitive advantage. These are inventions, optimizations, or intellectual properties that differentiate the company from its competitors. This is how the company is making or plans to make profits. Generic subdomains are the opposite. These are the solved problems. Here we have to solve a problem to implement some functionality, but a solution already exists. We can just use it. For example, we can buy an off-the-shelf product, or we can adopt an open source solution. We can just use it. We don't need to implement it in-house. Now, since that solution is available to everybody, there is no business differentiation here. There is no competitive advantage in generic subdomains, unlike the previous case of core subdomains. And finally, supporting subdomains are somewhere in the middle. Here, there is no ready-made solution that we can use. However, they also do not provide any competitive advantage. The best way to describe them is these subdomains are something that the business would love to be generic, but it's not. Therefore, they have to roll out their own solution. So supporting subdomains, they have to be implemented in-house. However, the biggest differentiation between supporting subdomains and core subdomains is since there is no competitive advantage here, usually supporting subdomains are much simpler. They can be implemented with simpler tools. And again, since there is no business differentiation here, they will get much less attention from the business. In other words, much fewer changes than core subdomains. That makes core subdomains the most volatile. Business is interested in changing them frequently to optimize its business performance, to increase its competitive advantage. So a core subdomain is going to change way more frequently than generic and supporting subdomains. So when evaluating coupling between components, it's also important to assess the expected rates of changes in those components, and you can do it by analyzing the subdomains that you are working with. And these are the three dimensions of coupling. They describe the nature of a relationship between two connected components. So we have strength, distance, and volatility. Now let's see what insights can we gain by combining them together. Let's start with strength and volatility. The higher the strength, the higher the probability of cascading changes, right? That's the definition of strength. Now, the higher the volatility, the more often we will have to take care of those cascading changes. So when both are high, we get a high maintenance effort. Strength and distance. Distancing the components physically increases the coordination effort that is needed to implement a change that affects coupled components. High integration strength over high distance makes the system expensive to change and to evolve. And finally, distance and volatility, these two reflect the coordination effort that is needed to evolve the system. If both are high, expect communication overload. Frequent communication between different and probably distant teams in the company. So these are three combinations of two dimensions. Now, that's still not the whole picture. To get the whole picture, we need to combine the three dimensions together. And combining the three dimensions together allows us to estimate the pain we're going to endure by maintaining that relationship. Now, I prefer to use the term pain because it's vivid, it's funny, but more serious people usually call it cost of coupling. You can use either one of them, pain or cost of coupling, same thing. So, stated simply, we can evaluate that pain or cost simply by multiplying the strength of the relationship times the volatility of the relationship times the distance between the affected components. And that means that if all these three values are high, the pain that you're going to go through is going to be high as well, right? Now, following this mathematical reasoning, and given that we're not interested in pain, we're interested in minimizing it, what should we do? How can we minimize it? Well, we can minimize it simply by making one of them 0. That's all we need to do to minimize, or in other words, to optimize one of the dimensions. Let's see some examples. First, if you can reduce the integration strength to minimum, contract coupling, then it's okay to have high volatility over high distance. Cascading changes are going to require lots of collaboration efforts, of course, but that minimal strength, it minimizes the number of such cascading changes that's going to happen. In other words, this relationship can be described as loose coupling. If, on the other hand, both integration strength and volatility are high, and there is nothing you can do about it, for example, let's say if the components are naturally functionally coupled, for example, something that, requires to work on the same data or to implement closely related business functionalities. In that case, you can minimize the distance. And again, those cascading changes are going to happen. However, once you minimize the distance, you put those coupled components close to each other. So when a change happens, it's almost like modifying one module. And this relationship, it is what we usually call high cohesion. We are putting together in the same boundary things that are going to change together. Again, that's reflected by their level of integration strength. That means that the integration strength cannot be reduced to minimum. There are some business requirements that prohibit you from going to the lowest level. You have to stay on functional level coupling, for example, or model coupling in some cases. And finally, if the volatility is 0, high strength over high distance, it won't really affect you. That's why, for example, it's okay to have intrusive coupling when integrating with a legacy system. Let's say that I have a legacy system in my company and I need some data out of it. Now, it's legacy, so it's not going to change. So it's okay for me to go and get the data directly from the database because it's not going to change. And me using its database directly, that introduces high integration strength, intrusive coupling. That system being a different system, that means that the distance is big. But again, that's legacy system, which means its volatility is going to be 0. So if the previous two dimensions were loose coupling, sorry, not dimensions, combinations were a loose coupling and high cohesion, then this combination can be seen as pragmatism. So to sum it up, the algorithm to minimize the pain is to first eliminate all accidental coupling, reduce the integration strength as much as possible. And again, you won't be able to reduce it to the minimum in all cases. Sometimes you will need higher integration strength levels. Once you've done that, once you've eliminated all that accidental coupling, or in other words, all that knowledge that shouldn't be shared between the coupled components, you can you can use that to decide what's the proper distance. If the integration strength is high, well, reduce the distance. If the integration strength is low, increase the distance. That's the principle of using 3 dimensions of coupling to minimize the cost of coupling, or as I prefer to call it, the pain you will go through when you will have to change the system. Now let's see a few examples. If we go back to microservices, I've seen many cases of companies riding that wave of microservices hype and deciding to decompose their monolith into microservices. And let's say, for example, they're using some smart decomposition strategy. For example, a microservice shouldn't be longer than 40 lines of code. I hope it sounds funny because it's a joke, but it happened in the past. Some companies tried that. So in that case, what's going to usually happen is the company is going to do a POC. Of course, they're not going to do a big rewrite, such a big change. Instead, they're going to do a little POC. They're going to extract a few microservices and they want to look how it's going to behave. And then they see that it works awesome. And of course, once that get that reassuring feeling that everything is awesome, they apply the same decomposition strategy to the whole monolith, and suddenly they find themselves with a distributed monolith. Let's analyze what usually happens here. That POC that usually succeeds, well, the company is not going to do a POC on some business critical functionality, right? They're going to do it with something that it's not that important. Or in other words, with a supporting subdomain. Or in other words, a functionality that has low volatility. So what they're doing is, by following that simplistic decomposition strategy, they're introducing high integration strength, they're introducing high distance because microservices, and in the POC phase, they have low volatility because of the supporting subdomains. But once they apply the same reasoning to their core subdomains, then suddenly they have high values for the 3 dimensions. They have high volatility, high integration strength, high distance, high pain. Another example is domain-driven design. Well, if we look into many, if not almost all, of the patterns in practices in domain-driven design, in one way or another, they can be explained with the 3 dimensions of coupling. For example, aggregates. Aggregates puts functionalities that require transactional boundary close to each other in the same aggregate. So what do we have here? Minimized distance, high volatility, and high integration strength. On the other hand, again, domain-driven design people usually tell that for a supporting subdomain, you probably can use some rapid application development framework. Supporting subdomains, unlike core subdomains, this is the place where you can round some corners. Why is that? Well, because the volatility again is low. By rounding that corners, we're introducing high strength, sometimes over high distance. However, because that's a supporting subdomain, that's still okay because the volatility balances that whole relationship. And as I already mentioned earlier, anti-corruption layer, open host service, or published language, these patterns are actually a way of reducing the integration strength between bounded contexts. So when we are dealing with multiple bounded contexts that have to work together, then we definitely have high distance. Now, probably we have high volatility there as well. And introducing one of these patterns reduces the integration strength between them. And with that, time to wrap this whole thing up. So I started with coupling, with the definition of coupling as simply saying that when two things are coupled, they are just connected. And coupling cannot be eliminated. It's an inherent part of system design, and coupling holds systems together. Now, to evaluate whether coupling works for us or against us, we can use the three dimensions of coupling: strength, volatility, and distance. Strength can be evaluated using the integration strength model. Here we have 4 levels that describe both the implicitness or explicitness of the integration interfaces and the type and the amount of knowledge they're sharing across their boundaries. Distance affects the coordination effort that is required to implement a change that affects both coupled components. So distance affects both a coordination effort, and it also affects the component's lifecycle coupling. And finally, volatility. This one describes how often the coupled components are going to change. And as I said, there are different ways to evaluate volatility of coupled components, Worley maps, but of course I prefer to use domain-driven design, and more specifically domain-driven design's subdomains. Core subdomains are going to change much more frequently than supporting or generic subdomains. Now, the 3 dimensions can be combined together to evaluate pain, the pain that you're going to suffer if you have to modify or to evolve that system in the future. Now, I want to add, since I still have plenty of time, I finished 10 minutes early, I want to rewind a few slides back and elaborate a bit more on this pain formula. So this pain formula, it reflects the cost of changes. However, it doesn't take into account other important things like complexity. Now, to talk about complexity, I would need another hour or 2. Of course, that's going to be covered in the book, but I just want to tell you that there is one exception to this mathematical reasoning here. Strength, volatility, and distance, one of them can be 0. However, you don't want both strength and distance to be 0, because in that case, you will put unrelated components in the same place, meaning you will produce a big ball of mud. So keep that in mind, and of course, in the book, there are 2 chapters about complexity and how coupling affects complexity, and the formula that's going to be described in the book will take this one a few steps further. So remember that again, strength times volatility times distance is the pain. However, make sure that you are not introducing both minimal strength and minimal distance. And with that, I'm going to fast forward to the wrap-up section and remind you, yeah, that's the book. That's my pain. That's the pain that I'm going through for 3 years now. So again, when it's going to get published, you will find there how that integration strength was formulated, how it relates to structure design and connaissance, and it will also, sorry, starting to lose my voice, and it will also describe degrees for each level of integration strength. So that, for example, if you have 2 integrations of functional coupling or of model coupling, the degrees allow you to compare them, to see which one shares more knowledge than the other. As I mentioned, the book is going to talk about complexity, and the notion of complexity will be used to elaborate that pain function further. Now, I mentioned domain-driven design a few times already. And if you are in Switzerland, then in December, I'm going to be there and I'm going to teach a class on domain-driven design. So if you want to attend it, here's a voucher code that will get you 10% discount. And of course, in that training, we'll talk about coupling and some of the stuff from the coupling book that I simply didn't have enough time to cover today. And with that, let's switch to the Q&A section before I lose my voice completely.
Wow, Vlad, amazing session. Thank you so much. We have a lot of questions here. Okay. Let's start with this question, the question of Valentina. What are some examples of desirable versus undesirable coupling you have seen in real projects?
Yeah, so all can be summed up with the pain function. Desired is the one that minimizes the pain, undesired is the one that maximizes the pain. And again, as I wanted to say in the presentation, the strength of coupling, that's what usually that's what is usually associated with coupling. However, that's not the whole picture, because even depending on implementation details, is going to induce lots of pain in one case, whereas in other cases it can be completely okay. So I would say I cannot provide any concrete example, but I guess we organisms, we have this pain avoidance for a reason, so we can just apply the same reasoning to software design.
Yes, it's a nice analogy. Thanks for that.
Thank you.
And you guys, if you have any examples, you can post them in the chat. Maybe we can discuss this one later. So, another question. You mentioned Worldly Map. Do you want to tell us something more about it? Because we had some discussion in the chat.
So Worldly Maps, it's a tool for mapping your business domain in the context of the or a wider industry that you are working in. And it uses other aspects that are not covered in domain-driven design. For example, it reflects the direction in which the industry is going. What functionalities are going to be commoditized, which means they're on the verge of becoming generic subdomains, and which can be used as a core subdomain. So in a sense, that's another way of looking at differentiating between the three types of subdomains. But it's a different outlook on the business domain. I would say that domain-driven design is more optimized for software engineers, but Worldly Maps is more about the overarching business, I've forgotten the word, climate, the business climate.
So, would you recommend learning it?
My friend Suzanne Kaiser, she is writing a book on combining domain-driven design and team topologies and Worldly Maps. So, of course, I recommend getting it when it gets published. Also, my another friend, Nick Tune, he completely writing a book on that touches on these subjects as well. And I think you can already pre-order his book. Architecture Modernization, if I remember correctly, the name of the book. I've read it already, and let me tell you, each day that passes and you are not reading Nick's book, you're losing some advantage over other people. So,
good to know. Great advice. Looking forward, and I actually really looking forward to your book. Do you
me as well.
So do you already know the release date?
Yeah. Every time I mention the planned release date, something happens and it gets rescheduled, so that's it. I'm not saying it anymore. All I can say is that manuscript is in the editing, which means a few more changes and it will go to the printers.
Oh, great. So looking forward. And talking about books, what are some resources to learn DDD for a beginner? Or let me rephrase this one. Would you recommend your book for beginners?
Yeah, so what do you expect me to say? Well, what I can say is when domain-driven design was introduced by Eric Evans almost 20 years ago, my God. So that wasn't a book that's easy to read. It was comprehensive, but it's heavy. It's a heavy book. So when I was writing my book, Learning Domain-Driven Design, my intention wasn't to compete with Eric's work or with Vernon's Implementing Domain-Driven Design. My intent was to write something that will make it easier to learn domain-driven design, to grasp the concepts. However, my book will take you from white belt to brown belt. To get black belt, you will need to read Von Vernon's Implementing Domain-Driven Design and Eric Evans's Domain-Driven Design. So, I don't know. I guess I answered the question. If not, you can see book reviews.
This is great. And there is another question from a senior software developer view. For experienced senior software developer aspiring to learn more on architectural design, system design, could you mention some resources? And it's about embedded software domain.
Yeah, those 4 words, embedded software domain, makes the question super interesting because when I was writing the coupling book, I had to take inspiration from lots of other sources from other fields like biology, city planning, etc. See how they're dealing with coupling. And it will be covered, of course, in the book's chapters. But interestingly, from what I've seen, it looked like coupling was already figured out in that domain of hardware engineering. Modularity in hardware is, from what it looks like, it's a solved problem. So I guess what I mean is the underlying principles that guide system design are the same, whether you're talking about an organism, a city, a car, or a software system. So I would say invest in understanding the principles of basic things. Modularity. How do you draw boundaries between components? Why one boundary will work for you while the other one is going to work against you? Learn about complexity. Why you want to avoid complexity, I guess that's clear, but how do you do it? And to give you a hint, these are the names of chapters from the decoupling book. Now, I feel bad for saying that, but you know what? Just a second. That's the book that I really, really recommend reading. Scale by Jeffrey West. I mentioned it tons of times in my other talks. It is about system design. So yeah, I would say read that book. It doesn't talk about software at all, but it will teach you a lot about system design.
It's great. Thank you so much. Here is actually an extension of this question. Embedded processors are getting high-end these days with cloud connectivity, database, etc. Probably generic resources on this topic would be also helpful in near future. So can you think of something else, or is it what you mentioned before?
Yes, I think I mentioned all I had to say on this subject because I'm not really into embedded processors. However, what's being described here is cloud connectivity, databases, etc. Our world is going towards a distributed computing more and more. Actually, if you look at the history of our industry, it can be seen as increasing distance over time. So In the beginning, everything was piled up in the same code base. Then we had modules, then we had objects, then we had services, now we have cloud. So distance grows, but in my opinion, the same underlying principles are still valid, namely the knowledge that being shared across different distances and the distances themselves, and of course volatility, and the three of them together, how to avoid pain in elevated amounts in a cloud system. Because by the way, Amazon released their Lambda functions, which are basically services. So what we have there is big distance by definition, so you have to be extra careful there about the strength between Lambda functions.
Okay, it's good. So let's go to this question, and this question is about a safe agile. In a safe agile software working environment where we incrementally create software components and requirements constantly change, and in many cases can't expect how many components are getting affected. And the actual question is any advice on design model?
Well, I will skip that safe part because I'm not the person to talk about it. However, the rest of the question describes a typical startup company. Yeah, that's what happens in a startup company. So, you know what? Give me a second. This book, Structure Design, a composite structure design by Glenford J. Myers, it was written in 70s. It explains, it talks about exactly the same problem that you described in this question. So I guess it further exemplifies that we're dealing with the same problems just on different scales. And again, the solutions are the same principles that were described here and in this book, modularity. If you have the goal of modularity is to contain changes, to design a system in such a way that the change will affect only one module instead of triggering a hell of other changes across it, and most of them unexpected, and a huge portion of them are discovered after a change goes to production. So that describes typical big ball of mud. The answer is modularity, invested in it. How, in my opinion, managing coupling, the dimensions of coupling. And again, something that has a dedicated chapter in the book is it's not enough to design the modules, to design modules one time. It's not something that you can do and forget about it. No, companies change, companies evolve, especially startups, but also enterprises, they change as well. That means their business domains can change, subdomains can switch their types, etc., which means architectural design, the design of the system or the design of module boundaries has to be adopted. Because again, a perfect design today may be a big ball of mud in a month, because changes in the environment and the business domain are going to invalidate all the work that was done. So it's important to keep your eye on that and incrementally evolve the design of the system. If you notice, for example, that today you have a low strength, high distance, high volatility, but tomorrow suddenly strength increases, that has to be addressed. The forces of coupling have to be rebalanced. So I would say that's my take on the requirements that constantly change and the situation in which you can't expect how components are going to be affected by those changes. I hope that answers that question.
It's great. And our audience are asking for the name of this red book again. Could
Which
you?
one?
A red book, the last one you showed.
You're not going to find it on Amazon or Kindle. Composite Structured Design. It's an old book. Yeah, and to be honest, this is the book from which I learned the most about microservices. Yeah, sounds funny. Book that was written 50 years ago. In my opinion, that's the place to learn about microservices.
Hmm. Alina, maybe it would be a good idea after the meetup that then Vlad could write down the title and the author name in case someone finds it on another
Yeah,
place.
yes, would be great. So after the session, we can post the name of all books Vlad is mentioning here. And maybe to come back to this question, do you have other experiences in this round, Nicole, Valentina, about changing requirements?
Well, I have, I guess, some examples when some teams they started too early into microservices, and let's say they didn't fully understand the domain and did the boundaries in the wrong way. And when they did the boundaries in the wrong way, then any change affected nearly anything. So basically, like distributed monolith. So I guess I see that as possibly a symptom that maybe the boundaries weren't well identified if we're constantly having to change absolutely everything. So I think it ties in with what Vlad explained about, are our boundaries right? Well, at this instance in time, but then also as time passes, to remodel the boundaries to minimize the pain.
So what what I see also with those microservices is that actually very few people, no, very few teams actually focus on the business. So they typically cut by something like, I don't know, this programming language already implements that rather easy, so let's create a new microservice for it. In your opinion, Vlad, what's the state of the industry in that regard? Because I think DDD doesn't seem to be very widely applied.
Yes, so it's depressing. Because when all this microservices hype started, people were saying that we're going to do SOA the right way. And SOA was driven by vendors, and now we're going to do it differently. We're going to make smart endpoints communicating through dumb pipes so that we don't need all that expensive infrastructure that they want to sell us. What they didn't think about back then is, I guess, Kubernetes, Kafka, and all that stuff that somehow, if you read the documentation, they're even saying that if you're using our tools, then you're working on microservices. Come on, let's be serious. We're back to SOA days where we have vendors that are pushing their tools and saying that this is the way to implement microservices. And yeah, in my opinion, microservices are great, but you need to have like high level of maturity or familiarity with your business domain. Otherwise, how can you make a decision how to draw boundaries? As Valentina mentioned, teams go and decompose systems into microservices, then they all change together. And why that happens? Because they didn't have enough knowledge about that business domain in the first place. So yeah, in my opinion, domain-driven design is a way to balance that craziness, to provide a more balanced methodology or guide or guidelines to designing boundaries of components. But yeah, I would love to see domain-driven design getting more attention, getting a wider adoption. However, now it is way better than it was 10 years ago.
Yeah,
Yeah.
I also think the book by Sam Newman, also the building microservices, also integrates into domain-driven design. I somehow have never heard anybody talk about microservices who understood what they did without including domain-driven design. Yet, whenever you go to teams, they're like, "Well, we do microservices," but
Yeah.
okay, but basically distributed big ball of mud in the end.
Yeah, so when this hype train started rolling, they were saying that microservices are bounded contexts. Like, these are the same things. They're not. Microservice, yeah, it is a bounded context, but the bounded context is not necessarily a microservice. And of course, what you call a microservice is not really a bounded context, because, yeah, we have plenty of those examples where a change affects dozens of services together. Of course, in that case, they're sharing way more knowledge than is, than we can allow in a microservices-based system.
Yeah, it's actually a very important note. And on this note, let's move to the question about microservices. Isn't it risky to implement strong coupling between microservices because they are maintained by the same team? What if the team expands and those microservices are assigned to different teams?
Hi, Felipe. That's my friend from Brazil. Yeah, just a second. I need to go over the question again. Isn't it risky to implement strong coupling between microservices because they are maintained by the same team? Yeah, so by strong coupling, I guess you mean that integration strength is high, distance is high because these are microservices. So yeah, of course, it's risky. It doesn't matter if it's the same team or multiple teams. I just use that example to exemplify that distance is affected not only by the boundaries, but also by the organizational structure. But overall, yeah, sometimes I do prefer to stay in wider boundaries. So for example, if we have one team and the same boundary of a bounded context can include multiple subdomains, which means there are no conflicting models there. If that's early stages of development of a project, yeah, I would strongly advise in keeping boundaries wider. But if when the company grows and suddenly you have multiple teams, then you can extract some of that functionality out of that wider bounded context into microservices or whatever you call them, or smaller bounded contexts. And by that time, your knowledge of the business domain is going to be way higher than in the initial stage. So I hope that answers your question.
So otherwise, Philip, feel free to post follow-up questions on this one. And we move to the next question. This one came during we were talking about contracts. And when you mentioned simple detail, could you explain again the meaning of it?
Yeah, so DTO is it's short for data transfer object, which is basically a very simple pattern. It describes a data structure that is used for communication. So let's say I have a business entity in my system called customer, and in it I have all the fields describing that customer and all the behavior associated with the customer. Let's say it's an aggregate. Now I need to share information about customers with, I don't know, some external component. Let's say external component that renders user interface. One way of doing that would be to expose my entity, that customer class or object or aggregate that I'm working with, and send it across the boundary of my service. What would happen in this case? Whoever is going to use my service, they're going to be aware of the structure of the customer in my system, how I modeled it, the model I used to implement that object. A simple way to encapsulate that knowledge is to introduce a data transfer object. A data transfer object is simply a data structure that describes fields that are relevant to the consumers of that service. So those fields can be different from the ones I'm using internally. For example, my consumers may be interested in much less data than I have. So the design of that data transfer object is going to be driven by the needs of the consumers. It's simply a translation from one data model to another one. One is used for my internal implementation of the business logic. The second one is used for integration. A really simple pattern, just transformation of data structures.
Thank you for answering this one. And let's move on. Let's go with this one. Could you please discuss runtime versus design time coupling and how it relates to the concepts you described?
Yeah, so runtime coupling is more about availability of components in the system. Let's say we have a distributed system and one component is down and suddenly the other components cannot function. That's runtime coupling between them. Now, in the book, I go much deeper in the discussion of distances to include that as well. To show how runtime coupling can affect the distance, because essentially what it means is if I reduce runtime coupling between components, it means I actually reduce their lifecycle coupling. That's just another manifestation of lifecycle coupling. Now, design time coupling, it's about boundaries. About the boundaries of your modules, and the modules can be everything. In the book, I use the term module for everything, from methods to microservices. It doesn't matter what type of an abstraction you're dealing with. Well, you have to design the boundary of whatever component you're working on, or a module. And that's basically design time coupling, and it involves evaluating the knowledge that you're going to expose across the boundary, whether what's the type of that knowledge, should it be exposed or can it be encapsulated? And yeah, together, again, multiple dimensions work together and they affect the pane. So in this case, in the case of this example, runtime coupling affects distance. It's just another aspect that affects distance. Yeah, I hope that answers your question.
Thank you, Vlad. Okay, let's move on. Could you please explain a bit more about the relation between module coupling and bounded contexts? And if I may, I would like to extend this question. Since we have you here, could you explain the difference between subdomains and bounded contexts, since it's sometimes a bit confusing in DDD community, or there is a lot of confusion?
Yeah, so one of the core tenets of domain-driven design is that to implement an effective system, we have to come up with an effective model that's going to represent the business domain. Now, that model, a model by definition, is not a copy of the real world. It just has to reflect what's important for us to solve the problem at hand, the problem that we are solving with our system. Another important aspect of domain-driven design is that we should work with multiple models, because in a typical software system, we usually have to solve multiple problems, implement different functionalities. And sometimes different functionalities are going to be addressed best with different models of the same business domain. Now, the model that you're designing, if you're designing a domain-driven design-based system, it can be used only, not in the whole system, but only in its context, where it applies, where it's effective. Or in other words, let's say that you are coining a model, you are designing a model, and you are defining its context, what problems it addresses, where it can be used. And that context is basically the bounded context. The bounded context is simply the applicability boundary of a model. A model should be used only within its bounded context. Outside of it, the same terms can have different meanings, or different terms can be used to represent the same meanings, because again, other problems are being addressed in other bounded contexts. Now, subdomains and bounded context. Subdomains describe the building blocks of your business domain. So let's say you have a company that works in retail. There are other companies that work in the same industry as well. Are you the same company? No. The companies in same industry are differ from each other. And the difference is in their subdomains. Those business building blocks, those fine-grained functionalities that are needed to be implemented in the system. Now, subdomains, as I mentioned, they have multiple types. Now, subdomains, they just a part of the business domain or problem domain, which means we're identifying them. Let's say you're working on a system. Let's leave aside for a minute startups. Let's say you're working in enterprise. So you have a business domain. You're analyzing that business domain and you're discovering its subdomains. They're a function of the business domain. You cannot design subdomains. You are discovering them. Now, bounded contexts are the opposite. You are designing the bounded context. They're your design decision. You can decide that one bounded context is going to include one subdomain or multiple subdomains. So the relationship between them is not one-to-one already. One bounded context can contain multiple subdomains, but also the same subdomain can be reflected in multiple bounded contexts because multiple models are being used to represent it. From here, going to Philippa's question about model coupling and bounded contexts. So again, a model is only applicable in its bounded context. That means that the internal of that bounded context assume the knowledge of that model, so they are model coupled by definition. Other bounded contexts, on the other hand, they shouldn't be aware of that model or depend on it. They can be aware of some parts of it, but not the whole model. That means that model coupling is totally acceptable within a bounded context, but it's not on a larger distance, but across multiple bounded contexts. And that's another aspect of balancing strength and distance. So within a bounded context, the distance is shorter than across bounded contexts. I hope that answers the two questions.
This is great. Thank you that you could combine them both. And we have 2 minutes left, so I suggest we move to the very last question. And this question is about coupling again. What do you think about availability coupling? If one component is unavailable, how it affects other components?
Yeah, so that's another aspect of lifecycle coupling, which is an aspect of distance. It's another property of distance, how components are integrated across the code base, how their runtime affects their life cycles. Synchronous or asynchronous communication can be used, for example, to play with the distance to make it virtually longer or shorter. Again, that's not the topic of this talk because it's too much stuff for one session. It will be discussed in the book. Maybe I will, put a new talk on those aspects as well. But overall, again, coupling happens in 3 dimensions: strength, distance, and volatility. Runtime coupling, or the dependence on the availability of components, it's one of the properties of distances.
So, thank you, Vlad, very, very much for this informative talk. I'm
Thank you for having
definitely
me.
looking forward to your newest book. And we have a lot of comments like this one. but you are also a great teacher.
Thank you
So
so much.
thank you,
Without
Vlad.
a voice, yeah, but thank you.
Uh, Great. So, and you guys keep following us because we prepared a lot of great sessions for you and following weeks. And stay with us on different social media platforms and keep learning how to deliver quality software faster. Have a nice evening. Bye bye.
Thank you.
Bye
Bye.
bye.